Okay, so we will start with time-independent perturbation theory. If you remember your quantum mechanics courses, most of the time what we had done was you had written down the Schrödinger equation, you had the time-dependent Schrödinger equation, or in the time-independent version, we had the E psi, H psi, where psi is the wave function of the system. So in principle, if we can determine the wave function of the system, we know everything about the system. Now, the problem is that there are only very few cases in which we can actually solve the Schrödinger equation exactly. I mean, if you consider the number of potentials for which are relevant for physics, for which we can find an exact solution. So what do you know? For which potentials? 1 over r potential, the Coulomb potential, we can solve. The harmonic potential we can solve. Particle in a box we can solve. Dirac delta potential we can solve. And kind of that's it. No other potential. I mean, we can solve some other complicated potentials, but they are not so relevant for the physics. I mean, if you 1 over r potential is the model for the hydrogen atom. The particle in a box is like the metals. The metals we can approximate as the electrons in the metals we can approximate their Schrödinger equation as a particle in a box. And the Dirac delta is again the electrons in a metal. You can just imagine the metal as we have a box, particle in a box, plus the potentials created by the nuclei. We can just model them as Dirac delta. That would be a simple potential. If you just have many Dirac deltas, you can even see the band structure in solids, which if we have time we will eventually do. So these are physically relevant, at least approximately physically relevant potentials. But even in these cases, there are many additional terms that we should add. We will see, for example, the hydrogen atom. Okay, we have the 1 over r potential, which is the potential for between two charges, but the proton and the electron, they are not just point charges, they also have what we call the spin. Furthermore, they are moving relative to each other, so these will all add to the Hamiltonian. So we will see eventually that we have to correct this 1 over r potential, take into account the fact that the electron has spin and also it is rotating around another charge. If we add those, we don't have an exact solution. But nevertheless, we should be able to estimate the changes in our system based on these potential, and that is what we will be doing in this perturbation theory. In fact, that is practically what we will be doing throughout the semester. How can we approach a given system if we cannot solve the potential or the Schrödinger equation exactly? What are the approximation methods? Now, in the time-independent perturbation theory, the basic what we do is we have the Hamiltonian, which we divide into two parts, let's say H0 and plus, or let's use the notation of your book, H prime. And we will assume that H0 we can solve for H0 in the sense that we know, let's write them in this form, is equal to E0 psi 0 m. We will assume that this H0 appearing over there, we can solve the Schrödinger equation, determine all the eigenvalues, etc., or the eigenfunctions. Well, in the worst case, what we can do is we can just take the kinetic part of the Hamiltonian, that we already know how to solve, and any other correction we can just calculate perturbativity. So in the worst case, H0 would be the kinetic term. But hopefully, like in the hydrogen atom, we already know the solution of the 1 over r potential. So H0 will involve the kinetic term plus this 1 over r potential. And then H prime will be due to the spin properties of the electron, due to the fact that it's moving around a positively charged object.
In order to add a perturbation, it should be as a smaller effect than the...
We will come to that. We will discuss that. Now, what we first do is we just write, let's say, H lambda say this is H0 plus lambda H prime.
What does the n stand for?
Now En, this En0 are the eigenvalues of H0.
Eigen functions.
And psi N0 are the eigenfunctions. So we know the solutions of all the solutions of H0. That will be our assumption. Now the H that we actually want to study is nothing but H1. Now we just introduced this parameter lambda. Now if we can solve for an arbitrary lambda, we can also obtain what H1 is. And that is what we want to solve. Now by introducing this lambda, it will be just kind of keeping track of the order of corrections. Whether H prime is 0, if the correction due to H prime will be 0, it will be proportional to lambda, the first correction. The second correction will be proportional to lambda squared, etc. In general, in practical applications, you don't even need to introduce this parameter lambda, because most of the time the interactions, they already contain some parameters, some coupling constants, some interaction strength. So we can just use that parameter. Now, as lambda changes, the wave functions will change, the eigenvalues will change in general. So if you want to write down the Schrödinger equation, time-independent Schrödinger equation for H lambda, the solutions will depend on, let's say, R, and it will also depend on lambda. And so will the energy eigenvalues. They will also be functions of lambda. Now kind of the tricky part, which is, well, it's not valid in every case, but assuming it will be valid, well, these functions, we will assume that they are functions of lambda. Furthermore, we will make the assumption that we can Taylor expand them in lambda. So this En lambda, we will just say that it is En0 plus lambda En1 plus lambda squared En2 plus etc. Well, of course, if whenever you make such a series expansion, you have to face all the problem of does this series converge? So if the series doesn't converge, I mean, what will you do? And at least one thing that you should check is if the series is convergent, that means the terms are getting smaller and smaller. So the correction due to this new H prime should get smaller and smaller as you go to higher and higher order. That is one thing you should check. But even that doesn't always guarantee the convergence of the series. In fact, most of the time the series doesn't even converge. But anyway, just keep in mind that we are making this assumption that the series converges, but nevertheless this assumption is not necessarily true. For example, in the electromagnetic interactions, if you study the electromagnetic interactions of electrons, let's say, if you calculate higher order corrections, what you see is they don't converge. Nevertheless, you can still obtain accurate predictions. There are other means which, well, you might study later on, but for the time being, we will assume the series converges, so we will be interested in calculating the first or the second correction at most. And we will hope that the first correction is smaller than the zeroth order term, the second correction is even smaller than the first order term. Now, if we do the same thing for the wave function,
is there a physical relevance in whether it converges or not?
well, you see, one thing about this Taylor expansion is that for here we are making an expansion around lambda is equal to 0. So that means that if you change, if you want to be able to make an expansion, if you change this, the point at which you are expanding, nothing should really change significantly. It should be changed very slightly. But if you consider, for example, the fine structure constant, we will be studying the hydrogen atom. If you make an expansion in the fine structure constant around the fine structure constant equal to 0, that is not a convergent point. because if that fine structure, whether that fine structure constant is positive or negative, makes a huge difference. If the fine structure constant is positive, the hydrogen atom is bound. If the fine structure constant is negative, then the hydrogen atom is not bound. So the two protons would be bound. So that makes a huge difference in that expansion. That is what we call an asymptotic expansion. It eventually diverges, but if you just cut the series at a given order, the next order gives you the accuracy. Now, if you expand the wave function, similarly, and now we can just put these expansions in our Schrödinger equation. So h lambda was h0 plus lambda h prime. Psi n is psi n0 plus lambda psi n1. Well, we will be interested in the first correction to the wave function and second correction to the energy. So let me just erase, no, let me keep the next one. Lambda squared psi n2 plus of the order of lambda cubed terms. Are you familiar with this notation? No. This is equal to En0 plus lambda En1 plus lambda squared En2 plus of the order of lambda cubed terms times the wave function. So on both sides we have polynomials in lambda, and these polynomials have to be equal, so they have to be equal order by order. So if you consider terms that are proportional to lambda to the 0, on the left-hand side we only have h0, psi n0. On the right-hand side we have En0, psi n0. Now this is what we call the unperturbed Schrödinger equation.
Is very small, around 0. Could we say that the higher order terms is, I think we're going to neglect it, right?
Well, you see, we put this lambda there just to count the orders, to compare the orders. The thing that has to be small is not lambda. You see, eventually we will be putting lambda is equal to 1. The things that have to be small should be lambda times psi 1 or lambda squared times psi 2 times lambda cubed times psi 3. They have to be small. We don't know what these psi 0, psi 1, psi 2s are. They can be also small. In this case, we will be, in fact, since we will be setting lambda is equal to 1, 1 is not small. But we are assuming that psi 1, psi 2, just like En1, En2, they are small. That's our assumption. Now, when we go to lambda 1, lambda to the 1, on the left-hand side we have h0 psi n1 plus h prime psi n0. This should be equal to, on the right-hand side, we have En0 psi n1 plus En1 psi n0. And of course, you can just continue like this. The second order correction, the third order correction, etc. Now, for the time being, let's just stick with this one. Let me change the notation slightly. I would rather use this notation. Are you familiar with this notation? I will be just switching back and forth. This is the first equation. The second one is H0. And the first correction to n plus H prime, the first correction to the 0th order state, En 0 and 1 and 1 and 0. And let me look at this one. Well, let's see. If you look at here, H0 is Hermitian, so I can just act it on the left or on the right. It doesn't make any change. But if I act it on the left, the first equation just tells me that that is En0. So on the left hand, on this first term just becomes En0. The overlap of the 0th order term and the first order term plus the matrix element of H prime on the unperturbed wave function. This should be equal to En0, N0, and 1 plus En1, and N0 is normalized. We will be assuming that the eigenstates are properly normalized. So on the left-hand side, on the right-hand side, the terms proportional to En0, they will just cancel. So we know what the first correction to the energy is. So we already know the first correction to the energy. Well, if H prime is a small perturbation to the system, then this En1 will be small, and En2 will be even smaller, so we can assume that the series converges fast, if H prime is small enough. Now we know now if you look at this equation over here, this one, or this one. So we had already, this was an unknown, now we know what it is. This we know. Psi1, we don't know, that is what we want to calculate. This one we know. It is a solution of this equation, which we assume that we can solve. This one we know. This one we know, the potential. And this is the one that we would like to calculate. So we can just combine everything that we know on one side and everything we don't know on the other side. And we would just obtain H0 minus En0 psi N1. This should be equal to En1 minus H prime acting on psi N0. This is just like an inhomogeneous Schrödinger equation. The only thing we don't know is psi N1. Now I can do one step further. H0 is a Hermitian operator. I know its eigenfunctions. And we know that if you have a Hermitian operator, its eigenfunctions are complete, in the sense that you can write all the solutions in terms of a sum of all the functions in terms of as a sum of the eigenfunctions of H0. So I can just say psi N1. Well, this is just a function. I can write it N1. This will be a sum, let's call an M, of the unperturbed states, because the unperturbed states form a complete set. Since it's complete, any function can be written in terms of that. Now, if I put it on the above equation, on the left-hand side, what we get is sum over A and M times, well, H0 acting on M ket just gives me EM0 minus EN0 this should be equal to times M. This should be equal to En 1 minus H prime and 0. This is 0. Now let's take the overlap with, let's say, K0. Now, in this sum, only the term M is equal to K will survive. All the other ones will be 0 because the M0 states are orthonormal. It is orthonormal. So the overlap, the norm of each one is 1, and its overlap with any other one is 0. So A and K, EK0 minus EN0. This is equal to EN1 K0 En1 minus H prime and 0. So we know these unknowns E and K. A and K. A and K is equal to K0, or let's see, En1 Kronecker delta Kn minus K H prime n divided by EK0 minus En0. Now, of course, this is true only if minus En0 is not 0. If this is satisfied, then we know what A and K is. Now, let's look at the denominator first. Now, up to now, N and K could be arbitrary, or N and K could be arbitrary. Let's look at this, this equation, and let's assume that N and K are equal. We look at the same state. So EK0 and En0, this is 0. And this is also 0. Why is this 0? Because if N and K are equal, let's see, this term is En1. This is N0, H prime N0, but that is also En1, the first correction. So these two terms cancel each other. So it's 0 is 0. So this term is 0, this term is 0. We cannot really say anything about A and N. This equation doesn't tell us anything about A and N. And if N and K are different, then already this is 0. We are left with this one only. So, okay, so let's say that A and K is equal to minus K0, H prime and 0 divided by EK0 minus En0, or this is our A and K, if N is not equal to K. Well, N is not equal to K doesn't guarantee that the denominator is non-zero. So it might be that different states have the same energy. So in that case, we are in trouble. We cannot use this one. We have to devise an alternative formalism. But if different states do not have the same energy, if the spectrum is not degenerate, then different states have different energies. So we don't need to worry about the denominator. And so we know the first correction for the nth state, A n n plus sum over all k not equal to n of Now, what to do about this A n n? So we don't know that yet. But you see, if we have n, now this is a differential equation for psi n1. So we have to somehow specify some boundary conditions, or specify some boundary conditions on our wave function psi n. And depending on the, in fact, let's say, depending, if you change the boundary condition, let's say if you just add some n0 contribution to your solution, if you have one solution, just add one more n state to this solution, and you get still the solution. Because the psi n0, this state, this contribution is the solution of the homogeneous equation. And this whole thing, this remaining part, is the solution of the inhomogeneous equation. So if you have one solution, just add the solution of the inhomogeneous one, and you get still a solution of your differential equation. Of course, it will satisfy these different boundary conditions. Now, what we will assume is that the boundary conditions we choose such that all these n0 contributions are already in the zeroth order state. So we are just adding all these n0 states to the zeroth order solution. So A and n is 0. We are just choosing A and n to be 0. And this kind of tells us what the first order correction to our wave functions are. So our exact solution is psi n 0 plus this one. Well, there's a diagrammatic representation of this expansion also, which are called the Feynman diagrams. I mean, the Feynman diagrams, you usually hear them for field theory, but even for for any kind of perturbation, you can actually use them. So what this tells you that, okay, you have your state will be, you have the zeroth order term, so this is your n state, or your state starts from the n term, and then h prime, the interaction there's some kind of a perturbation in the system. You perturb the system, and the system just makes a transition into a different state, unperturbed state, and then just continues living there. And this term, 1 over En0 minus Ek0, is what we call the propagator. Now the next term, if you calculate it, so this is, let's say, n, and there is one interaction, you go into k, or you start with n, one perturbation, you go into k, another perturbation, you go into k prime. You can just write it down. I mean, this will be part of your homework to derive the second order wave function correction, and you will see that the second order correction to your wave function will be, let's see, you are summing over all k and k prime. You started with n, there was an perturbation, and you went into k. There's a propagator. En0 is the energy of your unperturbed state. Then from the k, there's an interaction, and you go into k prime. And then from, you stay in k prime, k prime. This is the second order term. Well, this will be your homework to derive this. But once you realize that this expansion has such a structure, if you want to calculate, I don't know, the fifth order, just draw the diagram, and you can just immediately write it down. So now we have the first order correction to the energy, the first order correction to the wave function. Let's look at the energy correction, the second order correction to the energy. Again, we just look at this one. So here is our equation in the above screen for lambda. And up to now what we did was we just equated the lambda to the power 0 terms on both sides, lambda to the 1 terms on both sides. Now let's look at the lambda squared terms on both sides. Lambda squared terms. Okay, on the left-hand side, what do we have? We have H0, psi n2, and plus H prime psi n1. Yeah, psi n1 we already know. Psi n2 we don't know, but psi n1 we had calculated. And that's it on the left-hand side. On the right-hand side, the lambda squared terms will be En2 psi n0 plus En1 psi n1 plus En0 psi n2. Now, this is the coefficient of lambda squared. We have the, yes. Now, if the equality holds for all values of lambda, that's our claim. So we write h lambda and we find all the solutions for all the possible values of h lambda. So if for all values of h lambda that equation holds, so at every order, at every power of lambda n should have the same coefficient on the left-hand side on the right-hand side. That is what we are assuming. So if this assumption is satisfied, lambda squared terms on the left-hand side and lambda squared terms on the right-hand side would be equal.
It's like working on the vector space of polynomials.
Exactly. It's not like that. It is exactly that. Now let's see, we will do the same trick. We can multiply the left-hand, let's say, by n0. Let me rewrite it in terms of kets. We can multiply both sides by n0 on the left. If we multiply by n0 on the left, if you look at the first term on the left-hand side, h0, I can act on the bra rather than the kit. So that would give me en0 and the overlap of the 0th order term and the second order correction. On the right-hand side, I also have en0 times the overlap of the 0th order term and the second order correction. Well, the nice thing is I don't know the second order correction to the wave function, but when we multiply with n0, the second order correction, the terms containing the second order correction on the wave function, they cancel on the left-hand side and on the right-hand side. So what is left with is n0, h prime, n1. This is equal to en2. Now the overlap of n0 and n0 is just 1, plus en1, n0, and 1. And so we already know what en2 is. This is equal to n 0 minus n0 h1n plus en1 n0 n1. Now I will not substitute. We already know what n1 is. We had calculated it. We know what h prime is. We know n0. We know en1. Yeah, we know everything appearing in this equation. So in principle, you can just calculate en2 if necessary. And if you want, you can just continue like this. Once you determine en2, this equation over here is, you already know what en2 is. You know everything except psi n2. You can calculate psi n2, the second order correction to the wave function. And if you want to calculate the third order correction, you have to take the coefficient of lambda cube on the previous equation, take the overlap with n0. That would give you the third order correction to the energy. Once you know the third order correction to the energy, from that you obtain the third order wave function correction to the wave function, etc. And hopefully you get this series expansion, and you just hope that the series expansion, that each additional term that you calculate gets smaller and smaller. If it's not satisfied, there is nothing you can do. If it gets smaller and smaller, you can just hope that, if it gets smaller and smaller, you can determine what is your precision in your result, but still the accuracy, you don't really know. You just assume that once it gets precise enough, it is also accurate. But of course, that's again an assumption. Now, any questions on this one? Yes. This one over here, because I acted H0 on this one, it gave me En0, and this one over here, En0 and the overlap, this one. So I didn't write it over here. So this term is cancelled, that's why I didn't write it. This term is over here, This term is that one because n0 is normalized to 1. And I have this one. This one is this one.
Şöyle bir şey sorsam, H0'yu react H0 to what is on this right. Do we know what we get?
Well, that's, well, you know, once you obtain this one, just put it over here. You know this one, we already calculated this one, so we know this one, we know this one, we know E and 0. So actually you know. And in fact, since that way you determine what psi n2 is. Since you know how the H0 acting on psi n2, that's H0 acting on the right-hand side, we don't know that, but we determine what its action is, and we solve for that differential equation. If you want to know psi n2.
I understood this question. I just get lost. We, in the beginning, considered n0 and 1 equals 0, but then we define n1, and we choose a and n equals 0.
True.
So this one should also equal 0.
Well, you see, A and N, how we define it. A and N is the, so you are saying that this one is 0.
Yeah.
Okay, that's also 0.
So this is 0.
That's also 0. Fine. True. So this equation is even simpler. Now I can also write it down. So this is the solution for the second order correction. If you get lost, if something is not familiar to you, just please let me know, because for some of you at least it has been 1 year that you took your quantum mechanics courses. You took in different classes. So, I mean, if you are lost, just remind me. Okay, let's give a 10-minute break, and then we can continue.